Hi guys. So we finished up chapter or section 4.3 and we're moving on to 4.4 where we build quadratic models from verbal descriptions and from data. And here we're talking about mathematical models in the form of quadratics. And the properties of the quadratic functions can provide us important information about the model. So in particular, using quadratics to find maximums or minimum values by finding the vertex can be really, really helpful to us in several real world situations. So let's take a look at some applications here. We start out with a note. In economics, the revenue in dollars is defined as the amount of money received from the sale of an item. So that's the total income that you get from selling something. It's equal to the unit selling price, which we're going to call P in dollars, and multiplied by the number of units actually sold, which is X. So that is that the revenue is equal to X times P. In addition, in economics, the law of demand says that the P and X, the price and the number of units sold, are universally related. And as one increases, the other, or inversely related, it should say there, not universally related, inversely related. As one increases, the other decreases. We saw this recently on our exam, and I think we did one other example back maybe in chapter 3 related to this, probably under 3.6. So the equation that relates P and X is called the demand equation. So that's going to be the price in terms of X or vice versa. Let's look at an example here. So for the first example, we're going to, we have the price P in dollars and the quantity X sold of a certain product obey the demand equation. That is, P is equal to negative 1/6 X plus 100. For X between 0 and 600, that means I'm selling between 0 and 600 items. That's the range that this equation or this relation, the demand equation, is valid. We want to find a model that expresses the revenue as a function of the price. So remember we had R equals XP. So here, since we have P in terms of X, right, we can find R as a function of X is equal to X, which we have right here, times P, which I'm going to substitute in negative 1/6 X plus 100. And if I distribute the X term, I get negative 1/6 X squared plus 100 X. And that's where 0 is less than or equal to X, which is less than or equal to 600. So we carry around that domain restriction. So remember, this is our domain here. We can't go beyond that. That's the only place that our model is good for, because that's the only place where the demand equation is valid. Okay, so that's step A. That would be just this part, really. That's equal to R of X. The next part, what is the revenue if 200 units are sold? Since X is the number of units sold, then we want to find out what's the revenue when X equals 200. So we want to find R of X, or R of 200. Alrighty. So if we substitute that in, we have R of 200 is equal to negative 1/6 times 200 squared plus 100 times 200, which is going to give us negative $6,666.67. That should be a decimal. Plus 100 times 200 is going to be 20,000. So that's going to tell us that our revenue is going to be, if we add those together, $13,333.33. So that will be our revenue when we sell 200 units. The next question asks, what is the quantity that maximizes the revenue and what's the maximum revenue? So again, consider this. If we look at this function, we have r of x is equal to negative 1/6 x squared plus 100x. So here, a is equal to negative 1/6, which is definitely less than 1, or less than 0, sorry, it's also less than 1. So that means we're concave down. It means we have a maximum at the vertex. So at an x at the vertex and f of x at the vertex also. So to find the vertex, remember our vertex. We can find that at b over negative 2a and f of b over negative 2a. So to find the quantity, that's going to be our x term, which is this, and this is our f of x term, which is going to be our revenue in this case. So let's change that to an r of x. And I'll change the other one to an r of x also. All right, so let's work on finding our vertex. So x is going to be equal to b over negative 2a, which is going to be equal to, in this case, 100, because that's our b term, over negative 2 times negative 1/6, which is going to be equal to 100 over 1/3, which is going to be equal to 300. If I multiply both top and bottom by 3, this will cancel out. Okay, so when we sell 300 units, that's our x value at the vertex. We want to find out what our revenue is then at 300, because we want to know also what the maximum revenue is. So we've already found the quantity. So our maximum revenue is going to happen when r of x is, we have r of 300, which is going to be negative 1/6 times 300 squared plus 100 times 300, which is going to be at, if we add that all up, at $15,000. In reality, you don't really have a dollar come out of there. We can put the units on if we want to. So we have a max of 300 units at $15,000 is our R of X for max. Okay. So then what price should the company charge to maximize the revenue? So we already found where the maximum revenue was. We know what the number of units are, so we can say revenue is maximized when we sell 300 units. So that's X equal to 300 at $15,000. So when we sell 300 units, we can go back to our price is equal to negative 1/6 X plus 100, our revenue equation. And we can find out what price the company should charge. So we have negative 1/6 times 300 because we're selling 300 units plus 100, which is going to be equal to negative 50 plus 100, which is going to be equal to 50. So the price to maximize revenue. Will be $50. And that's the end of example 1. So you can see how we're using the vertex to find where we maximize the revenue and how many items we sell, how many units we sell when we maximize the revenue. And then we can use that to go back to our price equation from up here to find out what the price would be from the demand equation. Okay. Example 2,